Welcome to Algebra 1, Unit 6, Lesson 6-1, Rate of Change in Slope, Part 1. I'm Mr. Pilarski, and our objective today is I will be able to find rates of change. From that objective, you can see the part of the lesson, rate of change in slopes, that we're going to be talking about today are the rate of change. Part 2, we'll be talking about slope, which is very closely related to rate of change. Definition, rate of change. Remember, a rate is a comparison of two quantities measured in different units. Rate of change allows you to see the relationship between two quantities that are changing. If one quantity depends on the other, then the following is true. Rate of change is equal to the change in the dependent variable over the change in the independent variable. That's this ratio right here. I'm going to show you something. These words change in, you can use a triangle to represent that. We could write this as the change in the dependent variable over the change in the independent variable. That triangle is the Greek letter delta. I'll use that a lot of times instead of writing out the words change in the, change in. This is the Greek letter delta. It's the capital Greek letter delta. Probably should have made that a capital D. But anyway, we use this sometimes instead of the words change in. So the change in the dependent variable over the change in the independent variable is how we find the rate of change to compare two quantities in different units. Example 1T, finding rate of change using a table. Find for the data at the left, is the rate of change for each pair of consecutive days the same? What does the change represent? Remember, we just saw that the rate of change is the change in the independent variable, or the dependent variable, over the change in the independent variable. So the rate of change, I'm going to abbreviate it, ROC, is equal to the change in the dependent variable over the change in the independent variable. Now, a quick way to identify independent and dependent variables when you have a table. Typically, the first column is the independent variable, and the second column is the dependent variable. That's the way it's laid out. For one day, there's a charge of $60, for 2 days, $75, and so on. So we wanted to determine if the change in the dependent variable over the change in the independent variable is the same for each set of consecutive days. So on day 1, you're charged $60, and day 2, that's an increase of $15. We could go 75, take away 60 to get that 15, but that's an increase of $15. From 1 to 2 days, that's an increase of 1 day. Next, we have $75 to $90, which is an increase of 15. And also, from 2 to 3 is an increase of 1. So far, it's working out. It's a 15 to 1 ratio. From 90 to 105 is 15. And from 105 to 120 is an increase of 15. And we can see consecutive days here. From 3 to 4 is an increase of 1. And from 4 to 5 is an increase of 1. So the change in the dependent variable over the change in the independent variable for each set of consecutive days is the same. So to answer the first question, is the rate of change for each pair of consecutive data the same? Yes, it is. What does that change represent? Well, that change represents, if we set it up, the rate of change, the change in the dependent variable is $15. That comes right here. The change of the dependent variable for each set of consecutive days is $15. And the change in the dependent variable is 1 day. Now, if we were to interpret that, we could say $15 per day. So that's how it would be interpreted. What does that change represent? Well, it represents a $15 charge per day. So to write a little sentence to summarize our answer here, the answer to the first question is the rate of change for each pair of consecutive data is the same. Yes, it is. So yes. What does the change represent? The change represents a charge of $15 per day. So that's our first example with finding rate of change, and we used a table. Since we always graph the dependent variable on the vertical axis and the independent variable on the horizontal axis, the rate of change we defined earlier can be written as the rate of change is equal to the vertical change over the horizontal change, which is the same as saying the change in the dependent variable over the change in the independent variable. You have to make the connection that the dependent variable is always graphed on the vertical axis and the independent variable is graphed on the horizontal axis. So we're going to see how we can use this idea of vertical change over horizontal change in the next problem because it's given to us as a graph. Example 2t, finding rate of change using a graph. The graph shows the altitude of an airplane as it comes in for a landing. Find the rate of change. Explain the rate of change. Explain what the rate of change means. Should I put a question mark there? And this should be shows, not show. The graph shows the altitude. So we just saw on the previous slide that the rate of change can be defined as the vertical change over the horizontal change. So in this case, we have to go read and interpret the graph. We have 2 points chosen for us here and here. And this point is given by this ordered pair, 60, 1000. And this point right here is given by the ordered pair 180, 0. Now the vertical change is represented by the y values here. The y values, remember when you have an ordered pair is x, y. So the y values here are 1000 and 0. So to find that change, we subtract. So 1000 take away 0 over the horizontal change. Now the horizontal change here is 60 to 180. Starting at 60, we'd go 60 take away 180. One thousand take away 0 is 1000, and 60 take away 180 is a negative 120. When we divide this out, that gives us 8.3, or 8 and a third, because that 3 does repeat. So that's the rate of change, 8.3. Now, what does that mean when it says explain? What that means is we need to really figure out what the units are. And the vertical change is the altitude measured in feet. So in the numerator here, we'd have feet. So that would be feet here. And in the denominator, that's the horizontal change, or the left and right change, in this time measured in seconds. So that would be feet per second. So what this means is, oh, this does come out negative because it's a positive divided by a negative. So this should be negative 8.3, or 8 and a third. And what that means is that the plane, since it's negative, is descending or going down at a rate of 8 and 1/3 feet per second. So if we could write that out in a sentence, The plane descends at 8.3 feet per second. Now notice I didn't write this negative in here. It's because I used this word descends. If I'm expressing it just as a number or numerically, I would express it as a negative to indicate that it's descending. But as I write it out in a sentence, if I use the word descends, I don't use the negative there. So what this means is that the plane is coming down at a rate of 8.3 feet per second. This has been Mr. Pilarski with Finding Rates of Change, Lesson 6-1, Part 1. Thanks for watching. Bye-bye.